In this video, we're going to look at the shielding effect and something called effective nuclear charge. Now, there are some concepts in here that are really, really important, but there's other things that are not. And so I want to give you some clarity so that you can get through this section and feel like, actually, I do understand it. This little calculation with Z and S is kind of confusing, right? Okay, so first of all, the reason why the atom is a cohesive particle is the fact that the nucleus is positive and the electron cloud is negative. Opposites attract. So the electron cloud is attracted to the nucleus. That's what they're trying to show with these blue arrows on this diagram. The blue arrows are supposed to show that the negative electrons are attracted to the nucleus. Now, do you kind of notice too, like this blue arrow is like wider than these blue arrows, than these guys? They're trying to show Coulomb's law, which I'm obsessed with Coulomb's law. Opposites attract, yes, but the closer those oppositely charged particles are to each other, the stronger the attraction. So we had Coulomb's law in the middle of this previous sheet. And so D, distance, is in the denominator. F is like the attractive force between the particles. If I want to make F large, if I want a strong attractive force, then I want to divide by a small distance. And that's what happens when you put the particles close to each other. So the electrons that are in like the first energy level, the second energy level, especially like the 1s electrons, they're really close to the nucleus. And so they feel the strongest attraction to that positive core. As you move away from the nucleus, so maybe out into the third energy level and beyond, there's still attraction. It's just that it's a little weaker because the distance between the outer electrons and the positive nucleus increases. And so if I have, even though they're oppositely charged particles, but if I have them far apart from each other, that attractive force is weaker. Now, there are some repulsive forces. There's repulsion within the nucleus between the positive protons, and that's part of the reason why we need neutrons. Is they are kind of like peacemakers in the nucleus, that they help to kind of separate the protons a little bit. But there's also a little bit of repulsion between the negative electrons, and that's why, for the most part, within their orbitals, they kind of try to stay far apart from each other. But I'm most concerned with attraction. A lot of the properties that we experience in the lab can be explained by looking at the degree of attraction between the nucleus and the outer electrons. If the electrons are strongly attracted to the nucleus, then it makes the atom really stable. But if that attraction is weak, then we've got some highly reactive atoms. And so we want to be able to gauge the strength of the attraction between the nucleus and the electron cloud. Now, here's what's important. This thing called the shielding effect. When I think about a shielding effect, this is what I visualize in my head. I visualize like a positive nucleus. There's my positive nucleus. And here's a bunch of energy levels. 1, 2, 3, 4, what the heck, 5 energy levels. And then let's throw some electrons in there. And I'm not counting. I'm just going to like chuck some electrons in here. Electrons are negative. Electrons all over the place. Electrons, electrons everywhere. Okay, so we already said that obviously the electrons in the first energy level are closest to the nucleus. So they're most attracted to the nucleus. And as you get farther from the nucleus, that attraction just weakens a little bit because of distance. I mean, what did I draw? 1, 2, 3, 4, 5 energy levels. So those poor electrons out in the 5th energy level already show a weak attraction to the nucleus. Let's say I pick on this poor little guy. Whoa, he's so far away. This is already a weak attraction. Just because of distance. Now, on top of that, we add in something called the shielding effect. It's where all of these inner electrons, all of these inner core electrons, kind of form a shield. And they block the attraction even further between the positive nucleus and the outer valence electrons. So these are my core electrons. And like out here in the 5th energy level, these guys are my valence. These guys are my valence electrons. And so already it was a weak attraction, but now those poor little guys experience an even weaker attraction than what we maybe expected, just because all of those inner orbitals, inner electrons, block the attraction between the nucleus and the valence electrons. And so whoever called this the shielding effect, it was brilliant, because it is kind of like those core electrons forming a shield and blocking the attraction between the nucleus and the valence electrons, making the attraction even weaker than what we might expect. That's what they're trying to explain a little bit here. The amount of shielding an electron experiences depends on which orbital the electron is in. So obviously, like the 1s electrons never experience shielding. They are like the most inner electrons. There is nothing in between the 1s electrons and the nucleus. So they're the most strongly attracted to the nucleus. Even into the 2nd energy level, I mean, the only inner electrons would just be the 1s. So even in the 2nd energy level, like the 2s and the 2p, those electrons really don't experience a whole lot of shielding either. But once you get to the outer orbitals, that's when we talk about shielding more. Where, once there's a lot of inner electrons and inner orbitals, that's where the attraction between the nucleus and the outer electrons can be blocked. I like what they say in here too. Inner core electrons always shield valence electrons. But valence electrons do not shield one another. So, it's the core electrons that block the attraction to the valence. But the valence electrons are all the same distance from the nucleus. They don't block each other. Oh, okay. So I hope that kind of makes sense. That's what the shielding effect is. And everything that we talk about from here on out, like when we start looking at properties of elements and trying to predict patterns, I'm obsessed with the degree of attraction between the nucleus and the electrons. That's kind of where this shielding effect comes into play. Now, I'm going to be honest with you and say that I will never, ever, ever ask you to calculate this effective nuclear charge right here. It's fine, but I will never ask you to calculate it. Instead, I just want you to understand this concept of how we can gauge the degree of attraction between the nucleus and the valence electrons. And one thing we want to look at is distance. It's Coulomb's law. The larger the distance between the charged particles, the weaker the attraction. Then if I look at like a short distance, like my 1s electrons, when the distance between the electrons and the nucleus is small, then the attraction is large. The other thing I want you to understand is the magnitude of the charge. And so here's the example that they give us. And it's fine, but they're talking about calculating effective nuclear charge. And they show you this calculation for sodium, magnesium, and aluminum. And it's fine. I'll get over myself. It's fine. There's nothing wrong with it. It's that Z is really the number of protons, and S is the number of core electrons. And then you subtract them and you get this number, and the higher the number, the stronger the attraction. So when they say effective nuclear charge increases going across a row, like here they're showing us sodium, magnesium, aluminum. It's 3 elements that go across a row, across a period. And they're kind of showing here that effective nuclear charge increases. And there's like +1, +2, +3. And if you just look at the numbers, I mean, anybody can plug numbers in their calculator. I mean, you could obviously do this in your head, but it doesn't necessarily mean that you understand anything. And so I don't care that you can calculate Z effective, the effective nuclear charge. I want you to understand why attraction between nucleus and electron cloud increases. I want you to understand, like when we have this arrow and it's like, oh, the effective nuclear charge increases. Well, what the heck does that mean? I want you to know that as you go across a row or a period of the periodic table, the attraction between the nucleus and the electron cloud increases. And in fact, like, I'm not even going to go over this. It's not anything that I'm ever going to put on a test or quiz. Because just because you can calculate effective nuclear charge doesn't show that you understand like what it means or why we care about it. Check this out. Okay, so we already know that electrons that are closer to the nucleus have a stronger attraction. So distance, we know the distance thing. Now I want to show you what happens with magnitude of charge. And so for example, let's pick on all of these elements going across the third row of the periodic table. So I have sodium number 11, and then magnesium number 12, number 13 is aluminum, 14 is silicone, and then if I keep going across to like 15, phosphorus, 16, sulfur. Wow, these boxes are not the same size. 17, chlorine, and 18, argon. Okay, so sodium, number 11. That means that sodium has 11 protons and 11 negative electrons. Each time you go across a row, you're adding another proton to the nucleus, and you're adding another electron to the electron cloud. So by the time I go all the way across to argon, there are 18 protons, and there are 18 electrons. Okay, cool. I want you to know that Coulomb's law would say that as we increase the magnitude of the charges, and here the charges are going to be the charge of the nucleus and the charge of the electron cloud. It's the number of protons and the number of electrons. Which do you think is a stronger attraction? 11 protons and 11 electrons? Or 18 protons and 18 electrons? I'm hoping you said 18, right? It's just kind of like having stronger magnets. The more protons and electrons you have, the stronger the attraction. So I want us to know this. As you go across the periodic table, the strength of the attraction increases. We're going to say attraction increases. And if they ask us why is there a stronger attraction between the electron cloud and the nucleus in argon versus the electron cloud and the nucleus of sodium? We're going to say magnitude of the charges. We're going to say because argon has more protons and more electrons. It's a stronger attractive force. It's like a stronger magnet. Why do I care? It's going to affect the properties. At one point, somebody told me that the noble gases are non-reactive. But yeah, because if you go across the row, the noble gases have a really strong attraction between their nucleus and their electron cloud. And the more strongly those electrons are attracted to the nucleus, the more stable the atom becomes. Oh. That fact that the attraction between the electron cloud and the nucleus in all of the noble gases, it's a strong attraction. That's one of the reasons why they're not very reactive. That's what I want you to know about nuclear charge. I mean, if you drop that word effective, nuclear charge just means the number of protons. It just refers to like how positive is the nucleus? What's the charge on the nucleus? When you do this effective nuclear charge, that's when we take the protons and we subtract the core electrons. And really then it's kind of a measure of the attraction between the nucleus and the valence electrons. I'm not ever going to ask you to do that. But I will ask you, of sodium, silicon, and argon, which atom is going to have the strongest attraction between its nucleus and electron cloud? Explain why. And then we're going to say, oh, because argon's got more protons and electrons, the charges are higher, that's a stronger attractive force. Now here's the other thing that I want to mention. That somebody usually will ask, well, I get that we're adding more protons, but we're also adding more electrons. And so if we're adding more electrons, like, doesn't that make the atom bigger? And so we kind of know that, the nucleus really does not make up much of the space in an atom. It's like a marble in a NFL stadium. And so they'll say, yeah, we're adding a lot more electrons, so shouldn't that make, the distance, doesn't that make the atom bigger? But when you go across, look at what's happening. And so here, sodium has 1 electron in the 3rd energy level. Its highest energy level is the 3rd. Well, when you go to magnesium, you've got 2 electrons, but they're still in the 3rd energy level. Aluminum has 3 valence electrons, but they're all going in the same energy level. So the key is that as you go across the periodic table, yes, you are adding electrons, but you're just adding the electrons to the same energy level. So essentially that distance between the nucleus and the outer electrons, it's really about the same. Oh, we're just filling the 3rd energy level as I go from sodium across to argon. I might even put that note in here too. That D, the distance, remains, I'm going to say constant. Now, it's essentially constant. Eventually, we'll look at there are some differences. But for the most part, that D value remains the same because we're putting all of the electrons in the same energy level. I'll put that in here too. We're just filling the 3rd energy level. Now that might be different if we were putting electrons in different energy levels. Then yeah, I'm going to have to take the distance between the nucleus and the outer energy level. Then I might have to take that into consideration. But not when I'm going across. Then all my electrons are going in the same energy level. I'm just filling the 3rd level. So essentially they're the same distance from the nucleus. And so then the main reason why the attraction increases is because I've got more positive protons in the nucleus and more negative electrons in the electron cloud.